We are going live. We are live.
We are live. It's showtime. It's been too long. First of all, community, welcome back. I hope there's a decent number of people here. We haven't streamed in, how long's it been? A month? 4 weeks?
A little while.
Maybe three. Last time, go check it out. If you didn't, it was awesome. We had Usagi Electric on again, David. That guy is such a gentleman.
When's he
I really
sleep?
like him. Pardon?
When does he sleep is what I wonder.
Yeah, I just think he's chosen the life of a creator. He doesn't share anything really personal, but he doesn't talk about having a family or anything. So I kind of assume he's got a little more time because he's chosen that path, which is cool. You know, some people need to do that, or the world misses out on some amazing stuff. But either that or he doesn't sleep. Right. Designing tube computers through the night. So if you didn't see that, please go back and look at the last episode. It's exceptional. I'm probably going to bother him a little bit for some of the tubes he has to design. They were designed for computers, the 6AU6s. They're extremely high mu or high gain because the goal is to make logic circuits with them. That means inverters and buffers and flip-flops. And to do that, you don't want
a big linear range.
You don't want something in its linear, yeah, right? Yeah. And so, but that actually might lend itself to a nice high gain distortion guitar preamp.
Chopper.
So I'm going to try it out. I'm going to use some 6AU6s and see what I come up with.
Okay.
Anyway, speaking valves,
yes,
so I'm all about it.
So let me jump in real quick. We're going to talk about USB-C, the physical aspects today. I'm starting the journey of USB-C, but we're going to talk about a few things first. But we won't be talking about all the electrical modes and high speed and all that yet. We're going to start. We're going to crawl and then walk, and so that'll come up here second.
Yes. Yeah, we could end up doing multiple episodes. USB is such a
it's going to be. Yeah.
So and it's important to everyone. Right, we all use it.
Well, I was a bunch of us are holdouts. We didn't want to take the USB-C dive yet because honestly, that connector is a pain in the tail to work with.
It sure is.
Yeah,
it was designed first and foremost for the end user, and I get that. That's actually important. It's good to design with the end user in mind. But if you take that to its extreme, what you design and come up with from a product marketing standpoint is a teleportation device.
Yeah.
There's what you wish for and what's actually possible or practical. And us engineers, we're in between those two things, right?
Well, even the footprint, I get a footprint and I'm like, this doesn't work, and I had to make it work, and we'll talk about that.
Oh my gosh, Mike, you should, some of the modern microprocessors and microcontrollers are, even 10 years ago, I was encountering BGA packages where it's like, okay, the packaging engineer made it work for the die.
Right.
They were able to get it to work so they could release the product. Now the PCB designers who have to implement this are just scratching their heads going, this is not possible.
I think
our board is going to be expensive because we have to have 8 layers. Yeah. There's no other way to fan out this thing and get the power and meet all the requirements. Whereas it's like some chips, it's like if the package is designed, the footprint's designed well, you can get away with only having 2 or 4 layers if you're not using every feature of the part, and it will still function just fine.
Right.
But some of them, it's like if you're doing a 0.4 millimeter pitch BGA, heaven help you.
Yeah. Don't quote me on this, but I think Xilinx went through that with their Spartan 1 line. I think they ended up with a package that in SI terms just didn't make sense. And you couldn't get it to work at power, at speed.
I kind of feel like
they had to wait for a relay out.
I feel like every large semiconductor manufacturer's had one of those.
I think so.
In its line. And they're the parts they people try and they don't end up doing well, and they do a revision.
So yeah, to me, it all comes down to how open are you with your customers then about that problem, and that's the issue I had with one of the vendors. They screwed a friend of mine.
That's actually important too, because you know what? It's a career progression. If you're a good PCB designer, you might end up in if you do this for a career full time for big companies, and you go work for a semiconductor company, chances are you might get a job opportunity to move into package design at some point. And you'll be the one, because it's not the IP. There's electrical engineers who do IP and that, but then they work with the packaging team, and the packaging team are almost always, I've met some of these people, they're the kinds of engineers that go to DesignCon. They're almost always focused on signal integrity as the main thing, but they can get a job laying out the PCB that is actually the BGA, because you look at those, it's actually a really thin, really fine line printed circuit board interposer kind of arrangement with a flip chip or die bonded or wire bonded or whatever. So anyway, I'm going off, but so
you have a tube thing to show us.
Oh yeah, it's because I'm self-employed and I can kind of take whatever work I want. I've actually started, this is odd for a degree qualified electrical engineer, but it's fun and I love it and it's valuable experience. I've started repairing tube amps for my local guitar repair shop, which is kind of a boutique arrangement. They're pretty well known around here. And I got a boutique amp in as one of the first amps. It's a Mesa dual rectifier head. If any of you are guitar players out there like me, you'll definitely know what that is. It's one of the most sought after amps. They're made in California, in Petaluma, by Mesa Engineering. And they're called dual rectifiers, and they have a triple rectifier as well. It's kind of a modern classic because they have both tube rectifiers, which go in these sockets here, and you can see the problem here. And they have solid state rectifiers, silicon rectifiers, and you can switch between them and tell the sound difference. Like you can say, well, I'm recording this song and I want that real sag for a driven bluesy sound. So you can switch to the tube rectifiers, crank the power amp up, and the tube rectifiers, valve rectifiers, have a greater effective, what's called a plate resistance or equivalent internal resistance. And so when you really load them hard with it, like you've cranked the power amp up and into a dummy load or a massive speaker stack and you just hit a big chord, the power supply voltage sags. It's called sag, and it's a sought after feature of tube amps, right? Fender amps do it as well. Marshall amps don't, because they traditionally they only use solid state rectifiers, so they're really punchy, hard sound, and all the distortion in those is from the gain in the preamp.
Okay.
The Mesa, you can get some additional soft clipping from the power amp stage from this sag effect, right? And so they created this amp line where you could switch between them and pick whatever flavor you liked. This one had beer spilt on it, and it went down the side of the tube into the tube socket and underneath on the board. And guess what? Even FR, which stands for flame retardant, even FR4, if given the high enough voltage and right conditions and beer, which is a great conductor, by the way.
I only drink distilled water around my tube amps. Yeah.
In fact, you can use beer as a battery. You put two dissimilar metals in it as a strip, you put fresh beer in there, because it's acidic, it will give you a voltage. Yeah. So this thing totally blew up. So that's just some fun side work I've been working on. But Mesa couldn't replace this board. I called them every day for a week, and they kept saying, the guy that knows isn't around or is never available, and we can't get an answer. So I gave up. And milled one on FR1, which is more burnable than FR4, but but after I get all this, you know, the replacement sockets and everything soldered onto that, I'm going to spray the whole thing with a conformal coating. So hopefully it's more weatherproof, let's say.
You'll want to keep the conformal coating out of the chips, out of the socket.
Yeah, absolutely. Yeah. I don't want
they'll crawl if it
don't want them to crackle or anything. Actually, I'll probably I'll use masking tape.
Yeah.
I don't know. I'll figure out a way to do it. I might even conformal coat the board before I put the parts on. And hopefully if I get the soldering iron hot enough, I can have the solder melt through the coat. I don't know. What do you think's the best way of doing that, actually? That's a good question.
Masking the tube and staying clear of it. You know, I've done conformal coats with dips where you couldn't have any sockets or anything on the board, you know, which is problematic. But if you're doing a
spray,
just mask it off and know that it will crawl on its own. So if it gets to the edge of the thing, it'll crawl down in it over the next couple of years.
So conformal coat actually moves over time.
That's my experience. Yeah.
That's interesting. I wouldn't have thought that's new. That's cool, actually.
Yeah, that's been our experience, and that comes from the late 70s when I worked at a scale company. Where we had to be environmentally secure and yet precision analog, and yet couldn't have a failure mode. It was industrial.
Yeah.
Let's see what somebody just said.
RTV, I love that stuff.
Yeah. So we did things like that like make tight fitting connector covers and stuff like that if we had my memory.
Yeah.
So, hey, so I have
I've used that. Plasti dip.
Yeah.
Just full on clear epoxy, 2-part epoxy is another one. I haven't used an acrylic spray conformal coat. It was recommended to me by Mark Harris, who some of you may know who that is. He's another content guy, does articles for Altium, and cool guy, another Australian. He recommended this acrylic spray. So yeah.
Somebody said make sure you use electrical grade.
Yeah, I got it from Tech Tool or whatever that tool supplier is.
Yeah,
it's specifically for electronics.
So I have a through-hole board that was sent to me by Dave Plummer from Dave's Garage. We posted this in our Discord. By the way, if you don't know about our Discord, go to Coriolis-effect.com. Our Discord invites there. I posted the link to the video, but Dave gave me a very gracious shout out for helping him with a Pong. This is Coleco Telstar 1977.
That was a great video, by the way.
Yeah, it was. It was. So basically, his circuit had been meant, the resistor adder that made the pseudo NTSC signal was designed to go straight to a modulator. So I just showed him a common emitter buffer to follow it to create a 75 ohm output. So it wasn't much of a contribution, but it gave him a standard video output.
He gave you a good shout out, though. It got him across the line, and that was the thing, right?
Yeah,
that's what he needed.
Yeah,
because he, by original training, was he not a software developer?
Right. So he had done his previous board on one of the PC Easy CAD or something like that from one of the sites. And I said, try KiCad. And he did. So he picked up KiCad really fast. So
he's a very smart guy.
Yep. So USB-C.
What's up, Bill? What are you designing?
Well, I can't talk about the end product, but I made a sample product here. And the first thing I noticed was the USB-C footprint. And I started by going to Worthington Assembly.
Yes.
He's got
and I'm wearing my Circuit Hub shirt today. So, Chris, I hope you're watching. Chris didn't pay us, doesn't sponsor us. I'm just a fan. He's a great guy.
Right. Absolutely. and their contribution is not insignificant. Actually, Hackaday just gave him a good shout out. about like the perfect 0402 footprint. He talked about this when.
Oh, yes. I remember when he first wrote that article. It was actually quite a while ago. It was just before he gave me a tour of Worthington Assembly's factory. Okay. And they've expanded since then.
Yes.
They do great work. We were talking about head and pillow and some of those other assembly issues that you get. Yeah.
Right. So I started by going to his list of preferred connectors, and I went through a couple of them. And the first one I pulled up was this one.
Molex, of course. Yep.
I have no problem with Molex. The problem I have with this is it says pattern restricted area right here.
And what exactly does that mean?
I don't know, but it came in as a keep out. And it says pattern. To me, that means the copper pattern. They are saying don't use copper with solder mask over it, because if there is a flat piece of metal vibrating, it'll cut through it. I don't like to use, you can do it in low quantity. Don't get me wrong.
I would say
for high quantity, I don't like to use solder mask as an insulator.
But what is right there? On the connector?
It may be the metal shell. And I posted a 3D.
It's all metal shell.
What's that?
It's all metal shell right there.
It's a flat metal shell, so it may need a keep out. I don't know. And in the old days, and I may do this yet, is
I would put shield.
Call Molex and ask an engineer.
We should, but I would put shield copper right there where it says pattern restricted area that's attached electrically to the shell.
And these are shield connectors right here and here, so I wouldn't think there would be a need for it. So I didn't use this connector, because I didn't know. There's no room to route. And here's the problem. See this row of pins?
Yeah. How the hell else are you meant to break those out of there?
At 6 mil or even 5 mil rules, I can only get one via in this area and one trace. And the problem with USB-C is every connector is mirrored. So that means these lines are crisscrossing each other, and we'll show that. But down here in the corner, you can see D+ is on A6. Hopefully you can see that. Oh, can you see my mouse? Maybe you can't.
Yeah, I can. Yeah.
Oh,
let me remove that banner because it's obscuring the bottom part of the. And I want to point out one thing that may not be immediately obvious here, but the problem with connectors is you click a link that says data sheet.
Right.
It depends on the manufacturer or the website that you're on, whether it's DigiKey or whether it's the actual manufacturer website or who the manufacturer is. You can click on data sheet, and what it's actually giving you is not a data sheet. It's giving you a technical drawing, which is what we were just looking at there.
Right.
And you may not get all the context from the technical drawing alone. You probably won't, in fact. So...
And I had the opposite when I was looking for connectors. Is I got one that didn't show the footprint. It just talked about the connector itself, but I know the footprint.
But at least you can do through hole with USB-C.
So that's what I ended up doing. I went to a second connector. So I poo-pooed that one for now, since I did not call Molex and ask him. And I went to a connector that is half through hole and half SMT pad here.
Yep.
And you'll notice there's no keep out. So is the keep out problem real or not? I don't know, but this is the connector.
I don't think so. I think we would need to call Molex and talk to the person and say why.
Right.
Why is that there? Because chances are it doesn't need to be. Can we go back to that one?
Yep.
Because I just remembered another trick I learned years ago from Steve Howe, who's the guy who has a website, Apple Logic. I'm trying to talk him into joining us one of these days. But again, he's in Sydney, Australia, so the time zone is a problem. And
right.
He would be a great guest if I could get him. But Steve Howe would not just use solder mask. He would also use silkscreen. So if you need, if you're concerned that the use of a connector over time is going to cause a solder mask break, which I've never ever seen that happen myself. not with a consumer.
Yeah,
not with a consumer interface like USB, right?
Right.
Which is pretty small and doesn't really move. And if it does move that much, it's just as likely the user is breaking the connector off the board. But that keep out pattern restricted area, I would not put a keep out there. I would just add solder mask and silkscreen. I'd put a big silkscreen fill right under it because silkscreen's very thick and tough and somewhat more flexible.
Is there a maximum size? Oh, come on. Stop with the pop-ups. Oh, by the way, I turned off monetization on the site because it was only making $6 and causing lots on the videos as we stream them, and being a pain in the ass. So I turned that off for everybody. So yeah, I just pulled up the connector. You can see that we need to crisscross. Here's CC, for all the connectors. So I would not have thought to use the silk screen. That's very interesting. I would think that you wouldn't want too big a puddle of silk screen. Hang on, where am I? There we are. But I don't know. I don't know. You know, they can inkjet silk screen. They silk screen.
Yeah, it's as far as I've asked around a lot of manufacturers today, we still call it silk screen.
Yeah,
almost like literally every manufacturer I've spoken to about that has said, "Oh, it's actually an inkjet printer."
Right. Right.
And it's cured fast with a UV light, so it's hardened. It's like an epoxy. So yeah, you can use silkscreen, and it's still board layout. Board manufacturers will still remove silkscreen wherever there's exposed copper.
Right.
And the only reason they do that is for solderability. The machinery they have in the factory can put silkscreen
right across your copper
anywhere. Yeah. So if you needed it for some reason, you could possibly ask them to make an exception. Say, tell the front end, like, I know there's silkscreen over bare copper in these areas. It's intentional. Please add it to the board. But I mean, I can't think of a really legitimate use case for that. But there may be some, like when you're doing board artistry.
Right. Right. Like Kelly Heaton does.
Exactly. She probably has to put a lot of fab notes in to get the board fabricators to do what she's asking, what she has in mind. Right. So yeah.
So the second one I looked at, then let me see if I can find it.
I prefer through-hole USB connectors in general. I know that's going to become a limit for speed-wise for new generations. A through-hole connector, we're not going to get 40 gigabits per second. As it is, we're pushing it with just trying to get 5. But I've seen so many USB connectors snapped off a board that were the surface mount kind.
Right. Now, both of these have through-hole for the supports. This just happens to have through-hole for the second row.
Yeah, I guess. Well, yeah, I guess that does kind of mitigate the mechanical problem.
Yeah,
it does. Yeah.
So, so I go and I look and I say, okay, let's try this through-hole one. And I grab a footprint. The footprint matched this drawing. And the problem was that right here, it says the diameter is 0.65 mils.
That's not a diameter. That's an alignment. That's an alignment.
Hang on. You're doing
those. Okay, so go to the left. Go to the left.
Wait a second.
Okay, see the 0?
Oh, here it is. B is.
Yeah, that one. That one's your diameter.
I'm sorry. Yes, I had to blow it up to see it. So the diameter is 0.65, and when I went to the capability sheet for the PCB house we were using, it busted the minimum angular ring spec.
Well, that is a mechanical post hole. That's not a connected hole, right?
It is a connected hole. It's for the. So I might have been, and I fixed it, but I might have been worrying about nothing.
Can we go back to that drawing for a quick sec?
Yes, but I just wanted to bring up the minimum angular for JLC real quick here.
It's probably 10 mils.
It's so in mils,
a bit less.
0.13 mil.
That's not bad, actually. That's pretty tight.
Okay, so I did a spreadsheet. So hang on, let me see if I can show the spreadsheet here. Whoop. So it blew out the DRC when I set it to 0.13 mil. Altium told me, yeah, hey, that's no good. So and I tried a couple while I was guessing, and I ended up making myself a spreadsheet where the drill diameter is 0.4. That happens to be the minimum of the house also that we're using.
Yeah.
That's a pretty common number. And I had it so I could change the pad diameter. So when the pad diameter was 0.65.
Your minimum annular ring is 12.79 mils.
Yes, or 0.125 millimeters. Right here. This just changed right here.
Yeah.
Okay.
So
well,
are they just rounding
lower limit is 0.13.
Aren't they just rounding to 2 decimal places though? Like that rounds up. That rounds up.
Altium was kicking it out, right? And I swear by my DRCs.
I know Altium will be exact because it gets rounding errors down to like 6 decimal places.
Yeah.
Between them, but JLC PCB will probably be okay with 0.125. Well, they presented it as only 2 decimal places, and they're going to be plus or minus some percentage anyway. Right. They're going to be plus or minus 5%, or I'm just saying, like you could send it to them and they might be okay with it. I don't know.
So the problem becomes, you know, we use these online board houses and they'll make whatever you send them. But if you go through an assembly house that uses a professional PCB house, if you violate the standard, it'll cause a cycle where they kick it back and ask you. And you have to do this for everywhere you violated their standard. So I didn't want to violate the standard. And what I did was I found out that by making the annular ring 665, I had room for silkscreen clearance and met my spec of 0.13 here, because now I'm at 0.1325.
And this brings up another point, and I hope someone from Altium's watching, especially from the product management or dev team, because I've been wanting this for years, and all of their users have been wanting this for years. But, you know, you go into mechanical CAD tools are truly parametric. Any field, and Upverter, when it was a PCB design tool, had this one thing going for it. Everything else about it kind of sucked, but this one thing. Any numerical field you could put a formula into.
Yes, yeah, that's cool. That's cool.
It would calculate it for you. And they started putting some here and there in Altium, but the problem is it's all based on a Delphi library that's like 30 years old. So someone would have to go and fundamentally edit the baseline library and then make it, and then it would cause other things to break. So it's a difficult thing to do, and I get that. But it would be really, really good if any field in the whole software that takes a numerical value of any kind is also a calculator. That's just how it should be.
Right.
But maybe they did add that, and I'm forgetting, because the developers were talking about it right around the time I was still there, not 2019 or something. Maybe we could try it. Let's try it and see what happens. But in the meantime, yeah, so that's for the through-hole pads that actually connect to signals that you're talking about, right? Because the through-hole pads that are either end of those are for the mechanical, they're for the mechanical centering posts, and they don't have any copper. They should be unplated. And so there's a 0 annular ring on those.
Right, but these are signal connectors. But
the signal ones, right? So what's the hole diameter on those is quite small. You were saying that's 0.4?
0.4 millimeter.
but the pad size is 0.665.
0.665, and I set the solder mask expansion to 2 millimeter to 2 mil. I'm sorry, I work in both. I actually work in mils. I have to translate to millimeters.
So do I. And the annoying thing there too is because of all my experience designing boards and working at Altium, a mil to me is 1,000th of an inch, but in Australia, everyone else says mil, meaning millimeter.
Oh yeah.
Because they're lazy. And England, they do the same thing. They're lazy with the speech. They don't say millimeter, they just say mil. It's like, it's not 2 mils, it's 2 millimeters.
Don't get me going on microns.
Oh my gosh. But anyway, I can't change the whole nation I came from. It's probably why I don't live there anymore.
So this was my answer to the first part. Was I took the through-hole version, changed the annular ring, and then changed the solder mask expansion, and I'm passing all my DRCs now based where I punched the DRCs directly in from their capabilities list. It wasn't JLC PCB, but it pretty much matches like JLC or PCBWay. Those guys, they're a good, they have a good list of rules to follow on those sites.
Yes, they do. And there was a time back in the day when I was working with all of those sites to make templates for Circuit Maker that would have their default layer stacks and rule sets pre-set up.
Right.
If you go to Circuit Maker and you could take an OSH Park 4-layer and fork it if you know you're going to use their 4-layer process. And the layer stack and all the rules were already set up for you. Did the same thing with Seed Studio. I don't know if I didn't get through to JLC PCB because they kind of were competing with me with their Easy PCB or whatever it's called. Easy EDA.
Right.
Yeah. Anyway, so
what?
How do you deal with minimum solder mask sliver though? Because you've got some really, really tight solder masks.
They meet the. I think they're good for. Well, let me check the rule. So we go. Hang on. Back to the PC board. Design rules. There's my, if it has this footprint, change the, I'm
not seeing the rules.
Oh, you can't see the gray box. Oh, that sucks. Okay, so I won't be showing the rules. So right now the board is out being quoted, and I expect the vendor to tell me if I've got a sliver problem, but I passed my sliver rules, which is probably 1 mil.
Yeah, that's pretty small. The default sliver rules, something like, it's ridiculous, like 10 or 6, which is much larger than it needs to be.
Yeah, you can't. I couldn't even hook up some of my parts if I.
So here's the other thing. I had this conversation years ago with Chris Denny, who we mentioned already, from Worthington. I don't know if he's watching. I told him if he was watching us today, he'd be free to jump on and talk with us.
Yeah, that'd be great.
I don't think he's probably busy. Anyway, so Chris, I asked him, and I've asked other manufacturers this too. What should my solder mask expansion be?
I've asked him a couple times too.
It says 0. We'll edit it anyway, or the board fabricator will edit it and not even tell you.
And that's what I'm
just set it to 0.
Because
just set it to 0. And he said the same thing about paste mask. We're actually talking on the context of the right volume of solder paste at the time. But yeah, set it to 0. We will edit it if we need to based on our machine and the thickness of stencil that we know we're using. So, okay.
So, I went to JLC and I'm looking at their minimum solder mask, and they're saying to have a solder mask bridge, the spacing must be 0.2 millimeters or 8 mils. That's
it's pretty big.
That's huge.
So they are going to balk at your tiny solder mask slivers. But like you said, if you go to these Chinese fabs that have basically they sell to hobbyists mainly, but also, you know, quick turn prototype. They'll make whatever you send them.
That's right.
They just don't offer any guarantees that it's going to look good or work. Right. One exception to that, before JLC came along, before PCBWay even came along, I was using one of the first generation of those online quote automated fab prototyping services. It was the one Dave Jones used to always use when we were at Altium. He mentions them in some of his videos. What was they called? It was PCBcart.com. And I used to use them all the time, but they would reject things and have someone email me.
Right.
But they cost more, and then you realize that's why. They cost more because they've got people actually doing customer service and telling you when you have a problem.
Right. And checking. Well, you know, PCBWay and JLC, I think a human looks at every one of those, but automation too. Yeah. So
all of them have a degree of automation. That's right.
Yeah. So here is, I got a ground symbol in there somewhere. So what I wanted to show was that my intent is to use as I start out on this journey of USB-C, which, by the way, USB-C is the connector. It's not the protocols. It's not the speeds. It's a capable connector. But
right, the protocol is 3.1, right?
Right. USB 3.1 defines the protocol, for lack of a better word.
Now, in this case, you're only getting power from it and using the USB 2.0 functionality.
That's right. So even starting now, there is a spec, even when you're using these regular old data pins, which are normally D+, D-. Here they're shown as DP1 and DP2, because again, you have to have 2 for when the connector is mirrored. If you're traveling a large distance on your board, they really should be about 90 ohms.
Yeah. Yep. A 90 ohms differential, right? I thought it was 83, but
I kept finding 90 when I researched it.
Okay, 90. Yep.
Yeah.
You must be right. Yep. Is that the same for the new high-speed connections as well? Are they the same differential pair? Oh.
I don't think so. I think they're around 100, but don't quote me yet. I'll come back.
Okay.
Over 100.
100's easier because, you know, you get thinner traces and they fit better.
Well,
so that would make sense.
The problem I had was my stack up that was kind of just a default stack up. I couldn't get the trace small enough for 90 ohms. I was too close or too far away, whichever. I can't remember. But I had to go into I ended up making a stack up. So this is Altium stuff here, obviously.
Right, but you would go through the same process.
Hopefully my stack manager shows up on the thing.
No, not seeing it. It should show up because it's in a window inside the MDI.
There it is. So I did create an impedance profile. Hopefully you can see this. Let me.
Yeah, you got 90.02 ohms, so you're very close.
Yep.
With that's idealized with 5 mil trace gap, because that's the other thing. You could change your single-ended impedance, but change the trace width by changing the gap.
So somewhere along the line, I stopped worrying about differential impedance and treated it as 2 single-ended impedances, with exceptions. And that may not be right.
That's what Lee Ritchie would tell you to do.
Guess where I learned it from? From listening to Lee Ritchie talk. That's where you nailed that one. So I do.
Yeah.
Now, do I try and be mindful that it's differential? Yes, I do. Oh, well, here's another thing Lee Ritchie will tell you. Don't run them together because the same noise hits both. And at the crossings, you have the same noise. You know, if you're making an eye diagram, you have a pulse on both. He's like, run them randomly.
That's where Lee Ritchie stands apart from and differs in opinion from Rick Hartley and Dan Beaker and other, and even SI experts like Eric Bogerson, because the whole point of running them together is there's two reasons. And the main reason is to make sure they're the same length.
Same length.
Because
you need the same length. You need the phase to stay the same. Absolutely.
Yes, they have to maintain phase. But at multi-gigabit rates, if you actually look at a field solver and understand how the waves are, the energy is actually traveling,
right?
Then you get into a realm where you want to really take the opinion of people like Yuri Shlepnev from
Symborean or whatever,
Symborean Software, or others who actually really know the mathematics behind all this, but have developed the field solvers, because you can visually see mode conversion. And if you get mode conversion, you will have smearing of the eye, and your receiver will have a much harder time, and you will end up with a higher bit error rate. And the whole point of it is to get a statistically low bit error rate.
I'm actually looking for, there's some videos that show up my YouTube feed that I subscribe to Symborean. I'm saying it wrong, I know. Field solvers, but that shows the propagation of the field and how it goes through the vias for return path and everything like that.
Right.
So, hang on a second. My phone is ringing.
It never ends.
Yeah, it does. It's not a customer I recognize. So, where was I? So, anyways, I went ahead.
Created an impedance profile.
Right. And I picked again. I went to the capabilities page. Went to their common core sizes.
Mm-hmm.
Started with one of their common core sizes, which happened to be a millimeter. Here's an irritation. I have to switch, unless you tell me a different way. I have to switch back to the PCB to switch units, and then I can come back to the layer stack manager. And now
you shouldn't need to do that.
I can't.
It should work if you just click in the blank space and hit the letter Q.
I'm trying. Trust me, I'm trying.
But you've got a thing selected. I don't know if another way. Open the properties panel with nothing selected. Properties.
Yeah, hang on. Oh, I already have properties up.
It's probably on another screen or hidden
it's
somewhere.
On main. Yeah, see, it's not in the thing.
No, this is a bug. It's not a bug. It's an architectural defect of Altium Designer. When they built the new layer stack up manager, they created a whole new properties panel that's actually separate code from the normal properties panel.
Got it.
They made it look the same, but it's not the same. And the problem that causes from a UI perspective is that you switch to layer stack manager or impedance profiles.
Right.
And the properties, and the same problem happens in Draftsman. It's a different piece of code, and it was not meant to be, but it is. And so it doesn't open in the same place. It disappears, and it shouldn't. There should be one properties panel, and wherever you docked it, it should stay there, for God's sake. But they can't fix that easily. So
and see, under view, there's no change units under view. So the only way I've found to do it, so it doesn't bother me. I'm just
well, you can do it in the properties panel if you can get that to appear. That's the other thing that pisses me off about Altium is half the time. I love the tool. Don't get me wrong. Like, I'm an expert user, but there's this ongoing problem with panels that's been there since forever, and they cannot fix it. Is that with multiple monitors, which I always have, sometimes the panels just don't appear. They don't appear, and there is no way to get them onto the screen you're using.
Right.
Like, it forces you have to go back to a single monitor and go into the preferences and reset your layout. And so it resets everything back to factory default, and it's the only way to get some panels to appear. It's really freaking irritating. But anyway.
Right. It's powerful, so it's got idiosyncrasies is the way I look at it.
Yeah, and some of those idiosyncrasies, you just have to factor it into the cost of owning the tool that you will waste.
Right.
Probably 2 or 3 hours a year with little irritating things like that. And factor that into the cost of it.
Right.
Anyway, Sorry, rant over. Carry on.
Well, some people are talking in the chat here, and they're even talking about how the price and the cloud and stuff.
Yeah, I know.
So to getting back to this, I chose a common core, and then I found their preferred pre-preg thicknesses, and I made it a multiple of the preferred pre-pregs, and that's how I got my 90 ohms. So do I need to do that? Not for an inch or two, probably, but this was, since we're talking about the mechanics of USB-C, then the stack up is part of those mechanics if you depend on how deep you get into this. So here's the way I broke Altium. If I turn on, I changed the board size, but there was this predefined polygon. I can't edit the polygon. See, it's on the second layer, the layer 2.
Did you wait? Well, wait. Did you start with your layer stack having specific ground plane negative plane layers? Because that's where this could happen. Or are they signal layers?
The board out. It's outside the board outline, and I can change the polygon, but I can't edit this part at all here off to the right. See this funny shaded thing?
That's weird.
It is weird. And when
I have seen it before. Whenever I've had those things, which isn't very often, I just delete it and create a new one.
Well, I can't delete it, and so I go into to edit the board shape.
Wait, that you're saying that's a separate? No, don't do that. Don't do that. Let's see if we can see it in the Polygon Manager.
Okay. So where's Polygon Manager?
Go into 2D mode again. Escape out of that and hit 2. And go to Tools, Polygon Manager.
Oh yeah, right. Yes, that Polygon Manager.
Or TPM.
Yeah, it's there, but I can't edit it.
I can't see the Polygon Manager.
Oh,
really? You're sharing a specific window, not your screen, right?
Right, because the screen is just freaking huge. Hang on. Yeah, so it shows up in the Polygon Manager, but again, it's uneditable.
You should be able to delete it in the Polygon Manager, though.
Oh, I see what you mean. Thank you. I hadn't thought of that. Boink. Sorry, y'all can't see this, but actually, I can't find a delete for it. Delete, there it is. No, it just deleted the name, but not the.
Let me open.
Yeah, I can't delete the polygon in the Polygon Manager, but that was a great idea.
I'm opening another board on mine here to see.
Okay.
I can.
So, anyways, just kind of something I did. So let me turn that back off. So the first problem I had with routing is I can crisscross here on this layer, but I end up having a asymmetrical start to my traces.
No, if you right-click on the polygon in the top list in the Polygon Manager, there is a delete on the right.
Hit it, and all I did was delete the name. It didn't delete the polygon.
Well, for me, it deletes the polygon.
Oh, for me, it just deletes the name.
Probably because you had your cursor in the name field and not.
I tried it on the. We'll talk offline. I tried all variations on it,
okay.
And I tried it at the bottom of the polygon stack too.
Yeah, I'm in the beta. Maybe that's a thing they just changed.
It may be. So, anyways, this is how far we're going to get today. Is showing that we need to crisscross these lines. See, this is on the wrong side.
Right, because that whole connector was developed only with the user in mind, not with practicality.
Yeah.
Because the idea is you can flip it around and it works either way.
Right. But by the time I do this, I've got differing impedances on, and I wouldn't do it this way, to be honest.
No.
I fixed it a different way on my production board.
Wait.
Go ahead.
Yeah. I'm just thinking how I would Yeah, that's not easy, is it?
No, all you do is you move the twist around, right?
Well, and it forces you to have an extra via that you would otherwise not want to have.
Right.
And maybe at 480 megabits a second, it's probably fine.
It's probably fine. That is how I'm treating it.
But for all the others, you have to do the same thing. So I'm wondering if USB 3.1 capable semiconductors or microcontrollers or whatever, do you route just this single set of pairs, or does it take care of the flipping inside the chip? I don't know. I've never actually designed with 3.1 or USB-C connector before.
Right. This nearby, and that's why I say this is the start of my journey. So one of the things I could do is something like this. And each pair is now symmetric. So the blues run the same length on the same side, and the reds run the same length on the same side. Whoops.
You're still in a command there.
Yeah.
Yeah, that's
tricky. This gives me the chance to untwist them if I want. Or does it? It doesn't.
Yeah, I kind of think because you want signal integrity wise, you basically want them to be equivalent to each other. But the surface mount, this is a question also for FCI, who makes the connector, is they should have an application note that tells you how they recommend you route this.
I have been looking, and I've been posting them to our Discord, the user notes on a bunch of stuff that I could find. So again, commercial for the Discord. I've been dumping USB-C stuff up there.
Yeah, because the connectors come up with these things, but it's like, you expect us to do what?
Well, and another problem with doing this is you need a ground reference for the bottom, right? And a lot of times on a 4-layer board, the third layer is power. Well, power is not really ground, but we treat it like a low impedance plane. But Rick Hartley, I understand, is a fan of, if you have a 4-layer board, 2 ground layers and run your power,
Well, you have to, because otherwise you get unexpected loops. Because power, technically, like they'll teach you in engineering school, your power supply is as far as AC is concerned, and even with digital logic, we're talking about AC because we're talking about transitions, right?
Right.
As far as the AC is concerned, power and ground are the same. But when you route a board that way, you end up with all sorts of really odd return paths that you didn't plan for, because that assumption leads to things like, well, for this really to couple, it's going to couple to the power plane, but you've got splits all over the power plane because you probably have a 1V8, 3V3, and a 5VO. And that's one problem. The other problem is you're forcing high edge rate return paths to go through capacitors, which is kind of, well, that's what decoupling caps are for. That's why we call them decoupling. Well, they should be called coupling caps. Yeah, but they're not very good at high speeds. They're really, it's the plane-to-plane capacitance that gives you the capacitance you need for high speed. It's a very small amount, but it's high speed because it's low inductance. The problem is, in a 4-layer board, the two planes are a long, long way apart because they're around a core, which is maybe, 30 or 40 mils thick. So you have hardly any capacitance to work with. There's no point. You might as well make the inner 2 layers around the core totally ground, unbroken, and then run power as thick thick traces on your top and bottom layers, or polygon fills wherever you can make them on your top and bottom, and they give you a little bit extra capacitance. But that's how I do 4-layer boards. That's how Rick Hartley recommends it, and I agree with Rick. And he knows, he's got the experience to. He's tried everything.
So I want to get back to this question right here. Then the same noise will be on both evenly and cancel out. And we were talking about an eye diagram and talking about Lee Ritchie's. I don't want to call it his view, but it's his view as I understood it. Let me share something again. Stop screen. Present. Share screen. All right. So here's an eye diagram.
Yep.
Right. And what Lee said when I listened in on one of his talks was these are basically zero crossing detectors. That's really what we're after, is this ramp, this speed, the dVdt of both of these crossing each other at high speeds, right? And if you superimpose the exact same signal on both of these at the exact same time they're crossing zero, that's bad. You want them to actually be, the noise to be out of phase a little bit so the zero crossing detector doesn't get futzed around. So
I don't agree with that.
Yeah, I kind of do. I'm in the zero crossing camp.
I don't agree.
Okay.
That's not correct.
But that's
the whole point of a differential pair is that it is taking the difference between the two to say this is logic one.
Height. Yes, the height of the eye, right.
And noise superimposed on both is common mode, and both go up. The only case where what Lee's saying may apply is when the common mode noise is so egregious and loud that it is maxing out the true. There's a true and a complement, right? One of them in a diff pair, when one goes positive, the other goes negative, and opposite.
Right.
So whichever one is currently positive, if the common mode noise causes both of those to rise to a point where it's exceeding the input voltage for the gate, that is, let's say your input range for the input that this diff pair is connecting to, which is a comparator. The input of that comparator is its maximum allowable input is, say, 1.8 volts. And some common mode noise is it's actually going to be more than that. Let's say it detects a logic 1, anywhere above 1 volt differential. But let's say the maximum allowable input voltage on the pin is, I'm just making up a number here. Let's say that's 2.5 volts. It would take an insanely large common mode noise, right? So let's say your logic 1 is a good clean, if you've laid out the board nicely and you've got a good strong transmitter and high slew rate and the impedances are all matched. Let's say everything else is perfect. So you get your true signal goes up to, at the top of the eye, to a logic 1, which is going to be, what did I say? 1 volt,
right?
1.8 volts. Let's say we're dealing with 1 V8 TTL LVDS. So 1.8 volt. In practice, it's going to be something less than that because of loss. But let's just say everything's perfect. 1.8 volt. And your complement is at 0 volts, and they flip, right? And then the other one goes to 1.8. The other one. Okay. How much common mode noise, we're at 1.8 volt, how much common mode noise is required to make at that crossing point, which is halfway between, what's that? That's 0.9 volts.
Right.
Let's say we're at 0.9 and both of them are equal. Well, they're equal, so the input to the comparator sees them as equal, and it's going to mark that as that's a transition. So we're in the uncertain linear zone, but it's in the middle of switching.
Right. Exactly.
But
slot velocity.
How much common mode noise is required to exceed the let's let's go to that open part of the eye. Go back to there.
I found Lee Ritchie's the first time on the web.
At the middle of the eye, when you have a full logic 1 and your true is at 1.8 volt and your complement is at 0, how much common mode noise is required to cause a glitch or a problem?
It's the largest during the event. They're as far away as they can be at that time.
Yeah. You're going to need right there. For it to cause a problem, the input gate, and it's not shown on this diagram you brought up, the input to the comparator has clamp diodes. Even if they're not designed into it, there's an inherent clamp in the silicon because of the way they're fabricated, right? So you would have to get its power supply is at the input. Let's say the input chip is powered at 2.5 volts. You would have to have the voltage rise to 0.6 volts above that, which is 3.1 volts. You'd have to have so much common noise that your 1.8 volt switching signal is with a noise spike is suddenly 3.1 volts. It's more than double. If you have that much common noise coming into your PCB, you have other bigger problems.
Right. So what Lee Ritchie was talking about at the time that he talked about this crossing point, and again, I could have misinterpreted him. I don't want to put this on Mr. Ritchie, but he was also talking about 64 gigabit per second performance and whatnot, and it came across to me like he was really adamant about the zero crossing portion of it, not having those waveforms shift in time.
Yeah, that is actually true. Shift, that I agree with, because that's now we're talking. There is
a noise spike on the very rapid edge here that will make the edge, if there is 0.2 volts on it, that makes it look like what it would have in time without the spike. So it causes a jitter in there at the zero crossing point if the spike hits around the zero crossing point.
But this is also why they should be routed together, which is against
he says routed. Well, I'm sorry. He does say routed together in this one book. Yeah. And then I heard him say something different too.
He used to say they don't need to be routed together. They need to be the same length. But he was talking about under one.
I'm sorry. Yes. He says they need.
No, but here's the thing. They could be the same length and go different paths. And one of them is going to get more noise than the other. Just circumstantially, it is going to happen. And so you no longer have common mode noise. Now you have that problem he's talking about. So it's by his own words, it's like, no, they need to be routed together so that any noise goes to both of them.
He even said, and I'm pretty sure I got this right, that the vias can be randomly located. He used the word sprinkled, on the old SI mail list.
This one here, what you're talking about here is related. Yeah, this diagram here is a different problem. This is mode conversion, which I was talking about before. And Yuri Shlepnev actually shows a field solver visualization that's very compelling. It's real. Not the circuit, but the diagram further down is talking about the phase of a differential pair. You need to phase match as you go.
Right.
Again, if you're doing USB 2.0 speeds, 480 megabits per second,
this is not
on a board.
Yeah.
Like the distances are so short on a board compared to the wavelength, it's really not a big deal. But if you're doing 3.1 and newer, that's going to be a problem.
Right. So
I get hot under the collar with that discussion because I think a lot of people actually agree fundamentally. Where they get into arguments, I've been in a room where Lee Ritchie and Rick Hartley, who are both, in my book, both geniuses, and I really have a great deal of respect for both of them. We're just arguing. They get into an argument and shout at each other, basically. Yeah, it's hilarious.
And later, we're all at the Altium event. We're all sitting at the same table chatting away about making wine.
Right. They found their common ground.
Right. So yeah. And so my thing is, I'm not working near those speeds, so I can afford to be wrong about this. But if I had to work at 64 gig, it'd be a lot more research into.
Oh yeah,
that problem. And the other thing Lee Ritchie says is, how do you know? Right? Oh, they should be. Well, how do you know? Did you measure it? And that's his thing. He's very empirical.
Yes, that's why his talks are pretty compelling, and they're all based on actual measurement and evidence. So
yeah.
And Rick Hartley's are all based on real world.
Yes, I was going to say that. He is more the production guy. He came from the people that did StormScope, which avionics, L3 avionics.
Yeah, that's right. Yeah.
Yeah. And, the StormScope back in the 70s saved lives. It indicated to a pilot of a small plane that there may be a thunderstorm in front of you due to the lightning discharges before you could put forward radars on small planes.
Oh, wow. That's cool.
So he did the StormScope, and my boss had a StormScope in his Beach Bonanza. So
those are Beechcraft, those are the ones with a V-shaped tail, right?
That's right. They call them fork-tailed doctor killers.
I love that.
So his was not a fork tail, but it was a high performance craft. Yeah. So I hopefully I raised more questions than I did answers here, because that's the way I roll.
That was lively. That was lively. You got me riled up today.
Well, you hear me. I keep saying the way I interpret it, because I don't need an email from Lee Ritchie going, stop saying my name. No,
it's all. He's smart enough to know it's all publicity, right? So
right.
He'll be okay with it, I'm sure.
Well, the I don't want to call it an argument. What was an interesting conversation he had with one of the people that attended the talk was the old one about, is it energy or electrons? And he kept saying it works in a vacuum, trying to like get that across. And so he, getting consensus from a room full of SI guys, I don't know how often that happens, But of course we're all in the wave camp, the energy.
Oh, we are. Yeah. I mean, most people, once they get past high school science,
right,
come to eventually get to the realization.
Did you see the Verisum video?
Veritasium.
Veritasium.
I saw all the hoopla around it and all the replies and all the
Dave Jones replied.
Yeah, it kept coming up, and I kept telling myself I am not going to watch that. I don't need to. I have other things to do. I'm too busy. Right.
To shorten it, he said it comes on. A light would come on based on the distance between the connectors, irregardless of the length of the conductor. But what he fails to talk about is the amount of power that could jump that is based on the capacitance and inductance between those two conductors. The light would have to come on at a very small value for that to be true, instead of waiting for the DC current to go down and come back. That's the way I interpreted that. So
I haven't watched it, so I can't comment.
Yeah. We'll have an argument about it. I came here for an argument.
No, you didn't.
You're simply disagreeing with me.
No, I'm not.
No, I'm not.
Hey, 10 points to anyone who knows where that's from.
Yeah. Oh, I love their stick on the wines of Australia. You've
mentioned that to me before, and I think I've watched it, but it's been a while. I don't remember it clearly enough.
I just remember things like a wine that'll climb out of the bottle and beat the crap out of you type comments,
Yeah.
So
cool. Hey, well, we're already 10 minutes past the hour.
Yep.
Thanks everyone for joining us again.
Hey, some quick shout outs. VCF, April 14th, 15th, and 16th. I'll be there the 14th and 15th. Usagi Electric will be there. Ben, you couldn't join us this year.
I'm sorry. I know last year I said, I definitely want to go next year, and I meant to, but I have to visit my parents in Australia because their health is not the greatest. They're getting on, and they need some help. And I've got a bunch of junk at their house, the house I grew up in, and I need to get rid of it. So, you know, and it's the only time I could easily get over there.
Yeah, I hate that phase of life. I got to do that here someday. I'm like 64 soon.
Oh, you're very young.
Yeah, unless I'm trying to move a piano, then I'm.
No, don't do that. But still, you got a lot of good years left in you yet.
Yeah. So let's hey, real quick here, yeah.
And Johan, you're inspiring me. You know, I know what I should do is as soon as I can book far enough in advance, I'm just gonna make the booking and commit to it for next year, so I don't miss it.
So, the other shout out is PCBWay's having a contest. It got delayed by all kinds of things, including
Chinese New Year is not the least of them.
That was the last one, right? But they are having I'm a guest judge for their vote contest, which should be announcing pretty soon. So head over to PCBWay, check them out. Is my advice.
Yeah,
so, cool.
They do have some pretty cool. Every year they do have some pretty cool projects getting entered.
Yep. Right. Oh, final shout out for the USB-C is Hackaday's got a good series of articles on it. So check that out. And they talk about power negotiation, which we can talk about in the future, is how the protocols support 100 watts across these cables and 20 volts, you know, if you negotiate it correctly. So,
yep.
Very cool.
Cool.
All right, man. It's good. Great talking with you and great having everybody with us. And we will see you next video.
Yeah. Thanks, Bill. Enjoy your weekend. Bye, everyone.
You too.